Hi, everyone. Good morning. Hope things are going all right. So what I'd like to do today is proceed on to the next chapter. There are three axioms that we haven't yet discussed in set theorist use. Before that, I'd like to do I thought I'd just do one more exercise on some cardinal arithmetic. But then we'll move on to talk about the axiom of replacement today. I'll say a little bit, I'll do the exercise first and then come back to talk about how that axiom works. So let's do exercise 438. Oh, sorry, that's one of those on the homework. No, let me not do that. Let me do a different one. (441). So that says a real number is algebraic if it's the root of a polynomial. So the notation I had there was an x to the n. And each of the coefficients here, the AIs, are in Q. Show that there are uncountably many algebraic numbers. So in a sense, numbers algebraic is we can somehow define it using a polynomial. We can say it's a root of this polynomial equation, right? So potentially there are up to n roots there, of course, right? So the ones that we can define in analysis, there's only countably many of them. And the rest of the whole mass, vast sea of real numbers, the rest of them is uncountable. So deduce that almost all real numbers they're called transcendental. And that means simply not algebraic. When I say almost all, it means that the transcendentals are equinumerous with R. In that they, the transcendentals, are equinumerous with R. Okay. Well, solution, what do you say to this? Well, basically, you have to count the number of polynomials. After all, a real number is algebraic if it's a root of a polynomial. So if the polynomial is degree n, there are at most n real numbers here, right? If it's got real roots. Right? So each polynomial of degree n can only contribute at most n algebraic real numbers. So it's really a question of how many polynomials there are. And a polynomial, well, it's just determined by its degree n and then the sequence of rationals. So basically, the determining factor is the number of finite sequences of rationals. So every such polynomial is determined by a finite sequence of rationals. So I can think of that as a function, a finite function into the rationals, f0, f1 up to fn. So by a function f that goes from a finite natural number into q here. So this, recall, this is the notation for this is the union of all the functions, different natural numbers n into q. So the set of algebraics has cardinality. Well, at most, the collection of these finite functions into Q. And now you can appeal to an exercise. Sorry, you can appeal to a corollary. I think this is 429. I'll just check here. Yes. And use of 429 is here. This is countable. Right? So this then is just, well, this set is countable. Well, let me say. I use 429 here. Okay, which is Lf0, etc. So that gives an upper bound. So on the collection, the size of the collection of finite sequences, and therefore of such polynomials. So there are at most countably many algebraic countably many algebraic numbers. There certainly are infinitely many algebraic numbers because every rational is algebraic. So there are certainly infinitely many algebraics. As each rational is algebraic. Right? So we've got exactly omega many here algebraics. So the last sentence was about all of the others, the non-algebraics. Right? So then the cardinality of the transcendentals right? Well, this is R minus the set of algebraics. So this is an uncountable set, and we're just subtracting from it a countable set, and the result is still the size there of R. Right? This is exercise 421. Right? That exercise said you can't take an infinite set and partition it into two pieces of smaller cardinality. Well, here's an infinite set, and I'm partitioning it into the algebraics and R minus the algebraics. This has got smaller cardinality because it's countable, and the reals are uncountable. So the exercise says, if I take away the algebraics, I'm still going to have the same size, that of the cardinality of R left here. So this is 2D LF0. So the transcendentals are into one-to-one correspondence with the reals there. Okay, let's finish that one. Are there any queries? Okay, then let's move on to the next chapter then. So when Zermelo was setting out the axioms for set theory, this is in a 1908 paper, he omitted to, which he said later was sort of an oversight. He omitted one of his axioms that should have been there, the so-called axiom of replacement. And various people pointed out, Skolem and others suggested that his system needed the further axiom. So in his later work, of course, he did include this axiom. So it was most prominently suggested by someone called Frankel, Abraham Frankel. So set theory became known as ZF, Zermelo-Frankel set theory. There was Zermelo's axiom supplemented by the one Frankel axiom. But as I said, various people had suggested it besides Frankel. But that's how Frankel gets his name attached to Zermelo in terms of the formalization of set theory. So We're talking about the 1910s, 1920s now. And the idea of the axiom of replacement was that if you take a function and apply it to a set, you should just get a set. So you can't create a proper class out of a set. That's essentially the idea here. So it's a kind of delimitation of size idea. You can't get sets too big by applying functions to them. Why it's called replacement was that the idea is that you've got a set and it's a bag of things, and you applying the function is to the set means I look at the objects in the set and I apply the function to them. So I then get some other things, a collection of other things. And the idea is that collection of other things is another set, right, with these new objects in the other things. But if I think of a set as a bag, all I'm doing is replacing the objects in a bag by f of each of those objects, where f is my function. So what it looks like is something like the following. Here's my set X, and here are the things that are inside it. And I'm going to apply some function, right? And I'm going to look at applying the function f to X. So if this is u and v and w here, what I've just got down here is f of u, f of v, f of w. And if you like, you can sort of think of it as saying, here's the bag X, right? All I've done is in the bag replace each object by f of it. That's why it's replacement. So if X is any set, the range of f acting on X is also a set. Right, so again, get used to this notation, this kind of inverted commas applied to X. This is the set of T's for which there is a u in X and f of u equals T. This is also a set. And that's, as stated formally in the notes, I can think of f as any function from sets to sets. Then for any set X, f on X is a set. All right, so that's a full statement of the axiom. And I also write it out there in notation. It's a set of z's for which there is a u in X, such that f of u equals z. Okay, just to repeat this line up here. So examples of replacement in action. Let f of X be singleton of X. So the function from v to v here just puts a set inside a pair of brackets. Right, so this is defined on all sets. Right? So it's a function from V to V, all right. So if I apply f to omega, so omega, of course, is just the set of all the naturals. So this is just going to be this set. Which doesn't have any particular name. It's just another set here. But we think also the axiom is justifying that there are larger and there are sets that are results of our recursions. Right? So let f now be on an ordinal, it returns Aleph alpha. If x is not an ordinal, then it just returns 0. So again, I've got a function that's defined on all sets. So I don't really have to bother. I didn't want to bother about this bit, but officially the axiom talks about functions from V to V. So I just default to some other value here. So this says if I enumerate the alephs, right, in this way, this gives me a function f. So now when I apply f to omega, what do I get? I get the set aleph 0, aleph 1, aleph n here. Okay, good. But actually, it was precisely this set that Zermelo's original set theory didn't have. So he was unable to form this set of these finite alephs down here. So f on omega was not a set because he'd omitted this replacement axiom. So let's call this the aleph function here. In particular, he didn't have aleph omega, the supremum of them. So aleph omega did not exist in his theory. So this was just kind of seen as, I think, later as an oversight. So again, these are examples on omega. Again, let f of alpha be V alpha. If alpha is an ordinal, and let f of x be the empty set otherwise. So again, a function from V to V. And again, f on omega is then this, the finite Vn's here. So recall V0 is the empty set, and Vn plus 1 is the power set of Vn. We'll be looking at the V alpha hierarchy later. But anyway, on these finite Vn's, right, this is what F on omega is this set here. So again, in Zermelo's system, this set didn't exist. So nor did the union of the Vn's, which is V omega. Right? But you can remedy this by having the axiom of replacement, because then this then is a bona fide set here. So we need the axiom of replacement to justify things like this being sets. So this is sort of, typically it's kind of results of a recursion, right, which you want to be a set here. And indeed, we have used this axiom implicitly already. Typically in recursions. So an example in the text on page 55 talks about the proof of Hartog's theorem, which we're omitting anyway, so you don't have to pay attention to that discussion. So I'll just pick some other, I'll mention some other points where this gets used. So the fact that every well ordering is isomorphic to an ordinal, this also uses, well, the proof we have there also uses a instance of the axiom of replacement. So let me find this here. Lemma 319. So let me try. Okay. Hopefully this should be visible. So there was a use of the axiom of replacement here. This was the lemma. It was the crucial lemma for showing that every well ordering is isomorphic to an ordinal, which is the one that follows it. But here in this lemma, we were saying, looks like very similar to a proof of reduction. If every segment of a well-ordered set, initial segment of a well-ordered set, is order isomorphic to an ordinal, then A itself is order isomorphic to an ordinal. So what we did was assign to every initial segment A sub B determined by an element B of A, excuse me. So to each segment A of B, we assigned an ordinal f of B given to us by the antecedent there of the lemma. So we're assuming that every such segment here is isomorphic to an ordinal. Right? We argued that the ordinal was unique. So from a B, we've got an f of B. And then I just kind of said, well, let's Z be the set of these f of B's. So basically, it's the range of f on the elements B of A. And I think I may have said something quietly about it at the time, but the point is that at that moment, we hadn't introduced the axiom of replacement, and we hadn't justified that this is a set Z. So you could see there in a footnote that we're going to talk about this later. Right, so again, this is an example as in here. Here one had this well order, and we had for any B and A, there is a unique ordinal so that the segment of A determined by B is isomorphic to this ordinal. It is unique ordinal, let's call it alpha sub B. So then the axiom of replacement then justifies that there is this set here of these alpha B's. Because we have a function. So it is the range of f on A, where f is this precisely this function. F of B is AB, alpha sub B. Here. And we needed that at that point in the lemma because we wanted to talk about Z and show that Z itself was an ordinal. So that we could show that Z is an ordinal. Right? Not that it was the class of all ordinals. Right? So we used replacement there. So we also somewhat implicitly use replacement. When we do recursions on ordinals. So we define something like, we're defining what h of lambda is, and we are given some function f h of lambda is f of, well, the things we've defined so far. So again, I didn't mention it at the time, but we need this f to apply to a set. So I need that this is a set of things. Right? So I need to know that this is a set. I've applied the function so far recursively. But again, we've gone through, well, lambda stages. So I need to know that f of 0, f of 1, f of 2, and so on, all of these already exist as a set. And again, appealing to the replacement axiom gives this. So these are a number of places where the axiom is needed, right? Here. Another consequence of this with the axiom, right? So as an example, so there is no set x and no one-to-one function f, so that f takes the ordinals into x. Right, in a one-to-one way. So no such x, set x, no such function. Why? Because the function is one-to-one, I can invert it. So I'd have f to the minus 1 is now taking x one-to-one in the other direction. But now the range of f to the minus 1 is this proper class On. Right? So by Bernoulli 40, this is a proper class. Right? It's not a set. But x is supposed to be a set. Here's a function on a set, and its range is not a set. So this contradicts the axiom of replacement. So the axiom of replacement justifies this statement here. And what we did here for the ordinals is the same for any other proper class. C, say. There's no G and no set Y, such that G takes C 1-to-1 into Y here. Because I could just do the same maneuver. I could look at G to the -1 on the set Y, and by the axiom of replacement, this would have to be a set, right, rather than a proper class. Right? So G could be, for example, C. So C could be, well, it could be the cardinals, any of the other proper classes that we've come across. Not so many. Right? So it could be all sets, could be the Russell class here. So essentially that's what we have to say by the axiom of replacement. Usually we tend to, it doesn't crop up so often in our discussions. And so, I mean, in practice, you can ignore it for most of the time. But typically one application of it is this thing here, right? So you can expect perhaps questions to involve this idea with the axiom of replacement. Right? So check that you understand this.